So I've had several students ask me to help cover problems with wiring. So we're just going to go over some of the basics today, and we're going to start their ladder diagram. Line 1 comes into a switch, out of a switch, into a load, out of a load, home to the opposite side, in this case line 2. Now it's going to be 110 volts, so it's really line 1 in neutral, but we're going to have it simply as line 1 and line 2. So here's our power is going to start from one side. We're going to go back home to the opposite side. We're going to go into a switch and then out of a switch. We're going to go into our light bulb load, out of our light bulb load, and we're going to go back home to line 2. So what we're going to do is I'm going to start out where our map starts is line 1. Line 1 goes into our switch. In this case, I'm going to use this knife blade switch. The switch is open. So now that I've done that, I'm going to highlight this wire. I'm just going to put a little mark over here to know that that wire is done. It is complete. We don't have to worry about it again. Then we're going to come out of the switch into our light bulb load. So we're going to go into our load. That one wire is done. I'm going to highlight that one wire so when it's done. Now I'm going to come out of this light bulb load home to line 2. So we're going to come out of this light bulb load home to the opposite leg, line 2. Now when I highlight this, we now have a complete circuit. Everything is done. Now the next question is what happens when this switch closes? So if we close this switch, it should pass power. Right now the switch is open, so the symbol for an open switch is this. If I close this switch, the symbol will be this right here. So we're going to close this switch and we're going to see what happens. And we pass power, we have a complete circuit to our light bulb. We have a source, we have a complete path, and we have a load. That is a complete circuit. Now if I open this switch, it breaks the circuit. We're going to open the switch, we break the circuit. And this open switch opens electrons, just like a drawbridge. If you have cars stacked up and that bridge is open, nobody can go. Once this bridge closes, then the electrons can flow. And it doesn't matter which side you have a switch on. If you break any part of that circuit, you completely stop the flow of electrons. It's alternating current, changing direction 60 times a second. But as far as we're wiring, we start from left to right, top to bottom, just like you read, and it makes it simple. So when I open this switch, we stop the circuit. Now, I don't have to use just this knife blade switch. There's many switches we use in HVAC. One of the sayings I was taught is a switch is a switch is a switch. So I'm going to remove it from this switch. I'm going to move it over to a separate switch. In this case, I'm going to use this contactor switch. This contactor switch is simply 2 points. It connects from top to bottom. When I push this in, it closes it. When I let go, it automatically opens it. So we have one here, and I'm going to move it over to this switch right here. And move it over to this switch right here. So now we have a wire going into the switch and out of the switch. There's a separate switch on this side we're not worried about. I'm not going to use it. If you wanted to see it on the ladder diagram, it would look something like this. Notice it's not going anywhere. There's no wires going to it. There's no wires coming out of it. The second side of the switch is its own independent switch. I don't have to use it. I'm only going to use this one side. So the next question is, what happens when we close this switch? When I close this switch right here, it should pass power. So that's manually close this switch and it passes power. So this contactor is just another way of closing that switch. Now one of the issues we're going to have is I'm not going to sit here and manually hold this in every time the customer has a call for heat. And then when they get that house warms up, they release it and it shuts off. That's going to be quite a waste of time. So we need something else that we can use to control this. This is where our low voltage side is going to come into play. So what we're going to do is add a transformer to this. So we're going to take our line 1, come down into a transformer, which is an inductive load. Once we do work, we're going to then go home to the opposite leg. This is our high voltage side of our transformer, so we're going to wire that next. So line 1 goes into my transformer. So I'm going to take line 1. I'm going to go into my transformer, and this is 120 volts. That's the wire I'm going to use. I've done that one wire. I'm going to do this one highlight. Now I know the students out there, you guys hate highlighting this, but it is the key to making sure you've done everything. If I look at this, everything's highlighted except for this one branch right here. So what I'm going to do is I went into the transformer. I need to come out of the transformer, home to the opposite leg. So this one's going to go home to the opposite leg. So I'm going to put this wire right here. It's going to go home to the opposite leg. Now that I've hooked that wire in, I'm going to highlight it so I know it's done. Now I've powered up to my transformer. This is 120 volts going into this transformer. It can be 120, 208, 230, 480. There's many voltage you can work with, but in this case we have 120 coming in, and we're going to step down transformer, reduce this to a safe 24 volts. So there's fewer wires on the bottom side, and to make this accurate, we must also have these two lines drawn, which stands for iron core. And if we notice, the wires from the top never actually touch the wires to the bottom. It's stepping it down from 120 volts down to a safe 24 volts. We have a new source now. We went from 120 down to 24, so we have a new source. Now this new source is going to start out, we're going to go into a fuse and out of a fuse. Now the cool thing is, we've already mounted these fuses in here permanently. This is a 3 amp fuse. It's a blade fuse, just like you have in the car. This is the symbol for that fuse. Wire's going into it, then the wire's going to come out of it. Next thing we're going to go to is we're going to go to our thermostat, which is the letter R. From that thermostat, all that thermostat is nothing more than a switch. So inside that thermostat, we're going to have a switch. Coming out of that thermostat, we can control something. In this case, I want to control this switch right here. So we're going to come out of the thermostat, and this is going to represent a heater. So I'm going to use the letter W to a low voltage load. After we do low voltage work, we're going to go home to low voltage home, which is the letter C. So essentially 3 letters. R is 24 volt power, W stands for heat, in this case it's going to be our heat contactor, and then C is going home to the opposite leg. So if we see here, all of this is wired, nothing high voltage touches anything low voltage. So we're going to have our transformer go into the fuse. Now we're going to come out of the fuse. I'm going to come out of the fuse to my thermostat. So I'm going to come out of the fuse to the R letter of my thermostat. And if you pull the thermostat off the wall, you'll see the letter R. It doesn't have to be a red wire. It can be any color wire. The letter R is 24 volt power. So I've highlighted that wire. I know that's done. Now I know my W wire needs to go into this load right here. So I'm going to take my W wire at my thermostat and go into the load. And this is what causes some confusion with a lot of students. What load is this? Well, what we need to do is label this so we know that this load controls this switch. So I'm going to call this HR for heat relay. You can call it anything you want, as long as what you label it here, you also label it here. It could be this symbol, it could be this symbol, it could be this symbol, or any other symbol a manufacturer decided to use. There's no industry standard for that. So our W wire is going to leave the thermostat and go into the low voltage side of this. So this is going to be a relay. It's going to be an electromagnet in this case. This electromagnet load is going to control this high voltage switch, so I don't have to push it with my finger. On this contactor, the bottom side of this contactor is an electromagnet. If we see here, there's a coil of wire, so it creates an electromagnetic field. That coil of wire is going to pull in this contacts. So this low voltage side is going to be on the sides coming in here. On the high voltage side, it's a switch passing power. Low voltage side, it's a load, power consuming. So we're going to go into literally the side of this contactor. So this line wire W goes into the side. Now that one wire is done. We're going to highlight that one wire. Now the other side has to go home 24 volt common. So we're going to go home 24 volt common. And this is low voltage home. We have high voltage home, but we're looking for a low voltage home, back to that same transformer. And on the opposite leg, which is the common leg, I put that one wire in. We're going to highlight that one wire. Now everything is highlighted. That means everything is wired. Show you what's going to happen. If I energize the W terminal here at my thermostat, this switch is going to close, which is going to pass power to this low voltage load. This low voltage load is going to control this high voltage switch. And W. Yep. Put it on the wrong spot. This W switch energizes my electromagnet down here. This electromagnet closes the switch up here. So when I close this switch, this becomes a load electromagnet. We do work and go home. Then that closes this high voltage switch, which passes power for the light bulb to come on. So this contactor is essentially a heavy duty relay. Low voltage work controls a high voltage switch. So a trivia question is, what component is a load and also a switch? And the answer is a contactor. This particular contactor has a shield on it. If I take this cover off, we see that there's two separate switches. In this case, we're only using one side of the switch. The high voltage side, power comes in, power comes out. A separate switch, power comes in, power comes out. It's two separate switches. But if I take this completely apart, this is my high voltage switch. This down here is my low voltage load. This is my electromagnet. So on a ladder diagram, it's drawn as two separate components because really and truly it is two separate components. Down here is a power consuming device, low voltage, 24 volts, and up here is a power passing device, sending that power onto a light bulb. Internally, they're not touching each other. This electromagnet pulls against the spring, pulling these points down. The wires never touch. Same component, but they don't touch. So they're drawn separately, even though it's the same component, because wiring-wise, they are two separate components. So to show you how this works, I'm going to remove these wires, and I'm going to hook it up to this electromagnet of the one we took apart. I don't know if you can hear it in the video, but it's an electromagnet vibrating. I'm going to put this wire strippers up here against it, and that electromagnet is holding these wire strippers. When I de-energize the R and W switch of my thermostat, it falls down. It's no longer a load. When I open this switch, we no longer have a load. Now this load would no longer pull this in, and our light bulb, or our heater in this case, what we're representing, would shut off. So low voltage controls high voltage switches. So we're going to put this back over here. Not all contactors are 24 volts. For residential,